You are welcome back. The last time it was study session 9. Now we want to consider study session 10, and the topic is acids, bases, and salts. At the end of this study session, you are expected to have known how to define acid, bases, and salt as explained in the study. You are expected to know how to differentiate between a strong acid and a strong base. And lastly, you are expected to be able to explain the factors that affect the strength of either an acid or a base. Acid, bases, and salt are three main categories of chemical compounds, and these have certain defining properties which distinguish one class from the other. Strong acids are corrosive and they burn easily, while bases, on the other hand, they are the opposite of acids. They are bitter in taste and they are stupid to touch. Sea waters are detergents are some examples of substances that are basic. Many bases are oxide or hydroxide compounds or metals, and strong bases can also burn one's skin. Definitions of acids and bases. An acid are substances that when dissolved in water, they release hydrogen ions. Hydrogen ions is written as H with a charge of with a positive charge on top. While bases are substances when dissolved in water, they release hydroxyl ion. Hydrogen ion is written as OH with a negative charge on top. HCl, that's the commonest type of acid, is called an Arrhenius acid. And from the definition that we learned just a while ago, acid are substances that donate or releases proton. From here, HCl is releasing a proton. As we have seen, we have H plus and Cl minus. And when it reacts in water, this is showing a complete reaction, HCl in water. One hydrogen from HCl is being donated to H2O, now forming H3O plus, and the other component of the acid, the Cl minus, is coming out as Cl minus, as displayed on the slide. Another definition of acid and bases, it could be defined in another way. A substance that can transfer a proton to another substance or donate a proton to another substance is called an acid, while a substance that accepts the proton donated is called a base. A good example is as shown: HCl reacting with water, forming H3O plus and Cl minus. In this reaction, hydrogen is coming from HCl and is being donated to H2O. So by that definition, we can see this is called a Bronsted-Lowry acid, that is donating a proton to water. And in the final analysis, the water is becoming H3O plus. And the other example that we want to show as an example of a substance donating a proton is HCl plus ammonia, as in the second example. Hydrogen from HCl is being donated to NH3, forming NH3 plus. And the chlorine, that is the other component of the acid, is coming out. So we can now say that in the reaction of HCl with NH3, a proton is transferred from HCl to NH3, resulting in NH4 as shown. Strengths of acid and bases. A strong acid is a molecule that has a strong preference to donate a proton, while a strong base is a molecule that has a strong tendency or preference to accept the proton being donated. Examples of strong acid are HCl, HBr, hydrogen iodide, HNO3, and HClO3. And examples of bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. Periodic table and acid-base properties of compounds. Like I said earlier, the easier it is to release a proton, the more acidic the compound is. And that's the reason why the group 7 of the periodic table, they are highly acidic in nature as you move down the periodic table. And the bond strength, on the other hand, generally decrease as you move down the periodic table, and require less energy to neutralize the proton in an XH compound. That is, X stands for halogen and the H stands for hydrogen. Now, for any two elements that are bonded together, it's easier to break the bond and ionize the two atoms if there is a large difference in their negativity values. Then the electronegativity of element generally increases as we move to the right of the periodic table. Once we move to the right, the negativity increases. And as we move to the right of the periodic table beyond carbon, the stronger the acid for XH bond. That is what is observed. That is CH4 less than NH3, less than H2O, and less than HF as far as the acid strength is concerned. The pH scale. The pH scale is defined as the negative logarithm to base 10 of the hydrogen ion concentration. And mathematically it is expressed as pH is equal to minus log H plus. The type of bracket that is used in representing the H is a square bracket. And that square bracket is indicating concentration of the hydrogen ion. That square bracket indicates concentration of hydrogen ion. And another solution is 1, where we have an increase in that hydrogen ion. And if the solution is neutral, we are saying that the hydrogen ion concentration of 1 times 10 to the power minus 7 molar. Then an acid solution must have an hydrogen ion concentration greater than 1 times 10 to the power minus 7 molar. A basic solution is 1 in which the OH minus, because OH is the basic component, H plus is the acidic component. When it's greater than 1 times 10 to the power minus 7, we now say the solution is basic. A good example, a pH of 12 is indicating that it's a potent base, a very powerful base. Measurement of pH. How do we measure pH? pH can be measured using two different approaches. One is to be measured using pH meter. And what this does is it detects changes in voltage as a response to changes in pH. As the voltage changes, the pH equally changes. The other one is using indicator. Indicator dyes. They change color at different pH. A good example is bromothymol blue. It changes color from color yellow to color blue. Color yellow is at pH 6 and color blue is at pH 7.4. It is physiologically useful in detecting the nature of a solution, whether it's acidic or it is basic. The other good example is phenolphthalein. Phenolphthalein changes color from colorless, that is pH 8, to pink, that is pH 9. And this is very useful in acid-base titration in determining endpoints. Calculation of pH of solution of weak acid. This is very important because we need to know how to calculate the pH if you are giving information about the acid. If the acid reagent constant Ka for the reagent of hypochlorous acid is 3 times 10 to the power minus 8, the question is what is the resulting pH of 0.15 molar solution of hypochlorous acid? The first is to write the equation for the decomposition. Hypochlorous acid HClO, when it decomposes, it forms H plus and ClO minus, as shown up here. Then we can now write the acquisition constant. For them, that will be the concentration of each of the products divided by that of the reactant. So from that we have Ka equals to H plus, that concentration sign, ClO minus divided by HClO. Now, indicating H plus to be X, indicating ClO minus to be X, what we discover is, let me quickly say this, HClO, ClO, when you dissociate, we have H plus ClO minus. Earlier, I said this becomes H plus ClO minus divided by HClO. We have indicated the hydrogen ion to be X, ClO minus to be X. Now, if we are giving 0.15 molar of this as the starting concentration, we said for hydrogen is X, for ClO minus is X. If X of this has reacted, the amount left unreacted for HClO will now be 0.15 minus X, meaning that the amount that will be left unreacted will now be a subtraction of the X from 0.15. With this information, we can now substitute all these values in this equation, and these are shown up here. Ka, we are given the value from the equation, 3 times 10 to the power minus 8. H plus and ClO minus, we have indicated them to be X, and actually we are having X multiplied by X. and the other one, the coordinate left, is 0.15 minus x. So a careful evaluation of this gives a quadratic equation as shown, and that quadratic equation is x squared plus 3 times 10 to the power minus 8x minus 4.5 exponent minus 9. Using the almighty formula x equals to minus b plus or minus square root of b squared minus 4ac over 2a, we can find the value of x. When that was done, a careful evaluation gave x to be 6.71 exponent minus 5 and minus 6.71 exponent minus 5. Ordinarily, x cannot be negative, so we have to ignore the negative value and take to the positive value. So hence, our x is 6.71 times 10 to the power minus 5. You will recall that earlier I said the formula for calculating pH is pH equals to minus log of H plus. We have been able to get the value of hydrogen, so we now substitute that value into that formula. So the formula is as shown, pH equals to minus log H plus. Substituting the value of hydrogen, we have minus log 6.71 times 10 to the power minus 5. The kind of evaluation of that logarithm is minus 4.17. Minus minus gave a positive value. So the pH is 4.17. And going by the scale, this is an acidic pH. Salt. When an acid reacts with a base, the resulting product is salt and water. And the typical example is shown. HCl is the acid reacting with NaOH, that's the base. We're having NaCl and H2O. The NaCl is referred to as the salt, and that's the product formed. Thank you for listening. See you in the next class.